Welcome back to today's session. We are going to take a look. We are still looking at the back converter and doing the analysis of the back converter. We are going to take a look at the current through the back converter. So the last time we looked at the back converter, if I go up very quickly to show you, and we derive an expression for the voltage between across the load and the input and realized or came out with the same conclusion that it is the same as the voltage for a basic switching converter. What we need to find now is some few features of the current which is going through the inductor. We want to be able to find out the minimum inductor current to make sure that the inductor, the back converter is operating in a continuous current mode. We want to be able to find an expression for the average inductor current and also to find the expression for the maximum inductor current. So that's what we are going to try to focus on today. The input voltage we know fluctuates, and the input voltage, when it fluctuates or when it changes, our output voltage is also going to fluctuate, is also going to change. So if you look very closely, if my input voltage Vs changes, it means my output voltage is going to change. If I want to maintain a constant output voltage, then as my input voltage changes, I want to be able to modify my duty ratio to be able to keep an output voltage constant. So we can regulate our D, which is the duty ratio, even if our input voltage is not constant, to be able to obtain a constant output voltage. That's very important. Let me go back to the circuit very briefly, and then I'm going to explain how we got that. So if we go back to the back converter, and any of them should work, because we are going to focus on the node over here. So when you look at the node over here, we have IL, which is coming in. Let's go ahead and delete that. So this is IL, that's the inductor current coming in, and it's splitting into two. So we have IC, let's go back, and then so that's IC, let's delete that, and then we have IR, that is the load. So we have IC and then we have IL. So IL is coming in and is splitting across IC and IR, the load. So we know that if I write my KCL at this node, then IL should be equal to what? IL should be equal to IC plus IR. So that's my KCL. This is my KCL. We said that this back converter is operating in steady state, and one of the assumptions is that during the steady state operation, the average current through the capacitor is 0. So if we take this KCL and we want to find the average current, then the average current IL average should be equal to IC average plus IR average, but the average current through the capacitor is 0, which leaves us with only one equation. IL average should be equal to IR average. So that is what we had on the page I was before. So I'm going to go ahead and delete that, and then we are going to go back to our page. So that is how we are getting that. So we know that the average inductor current is the same as the average current across the resistor. If you come up here, this is why we have IR over here. So that is the inductor current. The average, we expect the average to be exactly in the middle of this change in the inductor current. And what we have seen is that the average IL is also equal to the average resistor, the average current through the resistor. So that's what we've just seen. The average IL is equal to the average current through the resistor, since the average current through the capacitor is 0. We know IL, right? We've calculated IL for the change in IL for two different scenarios, when the switch is closed and when the switch is open. We can use any of those expressions. If you look very closely, since the average is exactly splitting up the waveform, it means that if I know the average and I know the change in inductor current, I can get the maximum inductor current and also the minimum inductor current, because the average inductor current plus half the change is going to give me IL max, and the average inductor current minus half the change of IL is going to give me the minimum inductor current. So with that in mind, we can write IL max and IL min. So this I max over here is basically IL max, and it's basically equal to the average. So this is, we are using this to represent the average IL, and that is the change in inductor current divided by 2. If we pick one of the expressions which we obtain for the change in IL, then we can come up with an expression for finding IL max, which is the maximum inductor current. We can do the same thing for the minimum inductor current. So the average minus the change in inductor current over 2 should give us IL min. If we go to the other part of this page for the continuation of the notes, if we use the formula for the change in inductor current when the switch is open, and you can easily see that because of that, then we obtain the minimum inductor current. This can be simplified to that. So that is the minimum inductor current when the buck converter is operating in continuous current mode of operation in CCM. Now, how do we find out whether this I minimum is really not equal to 0? Because we need the I minimum to be a positive quantity. So some of the conditions we need to check to make sure that IL min is not equal to 0 is to equate this expression we have over here. So basically we want to take the right hand side. Let's delete that. We want to take the right hand side of this expression and equate it to 0, and then from there we can find different conditions which we need to have to make sure that IL min is going to be greater than 0. So let's go down, and then we are going to check some of those conditions. So when we do that, for the minimum current to be positive, we are going to come on to some few expressions. One of them, so that is the right hand side of the expression, equate that to 0, and one of the conditions is the product of the inductor times the frequency. The minimum of that should be equal to that. If we want to look at only the minimum inductance, then from this same expression over here, from the IL min expression, then we can find a condition for the minimum inductor, and when you do that computation, this is what you obtain. So we need the minimum inductor for the buck converter to be equal to that, with the assumption that our R, which means our load, is fixed and our frequency is known, and the D2 ratio that we are going to be using is also known. So with that, we can calculate the minimum inductor we need to make sure that we maintain continuous current mode of operation. We are going to end this, but before we do that, I want to show you some quick calculations I did where I obtained that. So if you go down slightly on this page, so that is the IL min. If you take the right hand side of it and say this should be greater than 0, and you try to do the maths, then we have a couple of expressions over here. This expression is telling us that that is the critical resistance, or the critical value of the load, in case we already know our inductor, we know the frequency we are going to use, and we know the D2 ratio. Then that is a critical value of the load we need to make sure that we are operating in CCM. to make sure that we are operating in system. So R, our load, should always be less than that for us to make sure we are operating in continuous current mode. We already have the expression for that, which is the product of L and F, which is on the page, and we also saw the expression for the minimum, and you can obtain all those expressions plus additional ones just from this inequality expression we have over here. So let's go ahead and delete this one, and that is going to end the session for this one, which basically we took a look at the various currents which is flowing through the inductor for a buck converter. So we now know how to calculate the average inductor current. We know how to find the minimum inductor current, and we know how to find the maximum inductor current. What else do we know? We know the conditions which need to be met to make sure that our buck converter is operating in a continuous current mode of operation. If we are looking for the product of L and F, then that should be the minimum value, okay, given that D is known and R is known or fixed. The minimum inductor, given that D, R, and F are fixed, is supposed to be equal to that. And also another one we can take a look at is the critical resistance, which means that our R, which is our load, should be less or equal to this expression we have over here, given that our inductor is fixed, our frequency is fixed, or our duty ratio is fixed, so that we can maintain continuous mode of operation. So this session is going to end, and we are going to continue in another session to be able to finish the rest of the notes on the buck converter. Thank you, and make sure you watch the subsequent lectures which are going to follow.